Okay, so let's move on. So this is the one that I told you about, this NO and PO here. The calculation, you have to know what is how to calculate NO, how to calculate ET, and the NCO value will be given. And then we have another one for PO. Then you have to calculate NV. This is the equation you have to know. Then what else? You know how to, you make sure that you know how to calculate KT, which is K is Boltzmann constant, T is the temperature. Then there's another question on NI. So make sure that you know what is NI. NI and PI, what is this equation, and what do you component you put in there, and what is needed in calculation of NI. Okay, like for example here you got this NI. You got this NI squared where you use NC NV exponential. Then you use your EG over KT. Okay, then you move on your square root, you get this answer. And then this is the quiz 3 and quiz 4, which is I already given to you. So if you can actually do it now, you don't have to wait. If you can do your quiz 3 and quiz 4, then you are actually prepared for your test 1 already lah. Then after this already, there's no more test 1 already. All this thing is you look forward for your test 2 lah. From this slide onward, what slide? After the quiz lah, dopant atom and energy level. So for your test 1 will be not so much, chapter 1 and chapter 4. For this doping, we already learned the doping concentration, why you want to dope it. We want to make sure there's more electron and make it more holes. Okay, then they got two type, N type, P type. Okay, then this is another one, the ion. Then intrinsic semiconductor is the pure semiconductor, but if you want to make some changes into it, you're introducing dopant, that is called extrinsic semiconductor. You have N type, you have P type, and when you try to define this, make sure that you understand to put all, the keyword here. So you have to mention for conduction band and you have to mention for valence band. Okay, so this is all right. We already saw this last week. For group 3, 4, semiconductor, how do you dope it? If you want to become N-type, what do you do? When you become P-type, what do you do? Okay, this is already covered. Okay, make sure equation is, you memorize this equation. In your exam, equation won't be given, so make sure you know them. It's all equation. Make sure you know both for NO, PO, for, and then another term is you're using this NI and EFI. So make sure you know what is NI and EFI. Okay. If you multiply NO and PO together, you'll get another term called NI square, which is we already done. So this is another term that you have to remember. This is important because for later on for your chapter 4 and chapter 5, you have to use this NO/PO equals to NI square. Product of NO equal is always constant for given material at a given temperature. So this is the homework that you can solve using F0. If you don't resolve F0, you can just show me any method you can do for your homework. Okay, this is the one that we did before we stopped last week. It's on Fermi-Dirac integral. It is shown here that if you want to do an integral of Fermi-Dirac where you don't remove the 1, if you remove the 1, you become Maxwell-Boltzmann. But if you want to solve this thing, there is an integral that already, you can get it from MATLAB code, you can get it a table, which they already solve it for you. Okay, this is called the Fermi-Dirac integral. So once it looks something like this here, they want to solve this. Okay, this is all the complicated one. You put it in all the component. In the end, you get, after substitutions, but you get something like this here. They will simplify this and they call it Fermi-Dirac integral. Where this one, if you put a half here, they say that Fermi-Dirac in order of half. Okay, those who took 4653, SKL 4653, you already encountered this. If not, if next semester you're going to take this subject, you'll see this again. How do you solve this? But here you just have to remember the integral, we replace it with a Fermi-Dirac integral, where you can, if you plot it, right? If you plot it, you get something like a blue line here. This is called Fermi-Dirac integral, order of half. Okay. Is there any order other than half? Yes, there is order 0, there's order negative half, there are order 3/2, there are many. But for the for NO and PO, for the 3D material, if you're gonna solve this thing, you are getting half lah. Okay, when are we gonna use 0 and negative half? Well, in the next semester, you'll be learning that if you take my other subject. Okay, so for here is half is good enough. Okay, it looks something like this here when you plot it out. When you plot this thing, and then they say that if you try to plot this curve, you find that in this region here, they are accurate. Another curve, but over from this side onwards, they are no more accurate anymore. They split. Okay, this is just trying to show you. If you want to substitute this with another expression, you can substitute with this. Okay, provided you are using the region here only, this region. Beyond that, no longer accurate. Okay, then another terms that you're going to face is called degenerate and non-degenerate. Very simple only. I will let you know degenerate means that highly doped, very highly doped, and non-degenerate is not highly doped. It's like doping concentration very quite low. Small amount of dopant. So you know that degenerate, if you dope it very high, then your EF will be very near to your conduction band, extremely near. But this is far away. So if you have small amount of dopant atom, impurity atom, then you have this condition. There won't be any interaction between dopant atom because they are far apart. They have non-interacting energy state because they're discrete, and EF at the band gap. What he mean here is that within the band gap here, you see, between here. But if you have large amount of dopant, then you have many of them, then many of them will be very crowded, then will interact with each other. Then the band of dopant widens and overlap the allowed band. So then EF lies within the conduction band. This is what in theory they say that your EF is above your EC or below your EV . But I would still believe if you draw your EF very near to your EC, is between here, it is still called degenerate but Niemann's way of to interpret it is say that is lies in the conduction bands and equivalent band . This is the definition lie between already down here. But for me, I will still accept if it's quite near. It is within the band gap which means very near to EC or very near to EV. So this is degenerate and non-degenerate. Another term you'll be encountering again and again is called degenerate and non-degenerate. It means the highly doped and low dope, lowly dope. So statistic donor and acceptor. So now they will introduce one thing here that if you want to cover the density of electron occupying at the donor state, density of electron at the donor state, ND. So if you got ED here, they want to calculate how much dopant here, then they'll be using some equation similar to here, where they say that number of concentration that you have and number of ionized donor that managed to jump to their conduction band, leaving behind positively charged dopant. Okay, that this is what it meant here. Then this is ND minus ND plus, and an expression, if you want to use this is the expression you can use, ND over 1 plus half exponential in bracket ED minus EF, ED minus your EF over KT. Then similarly, the same thing is for holes, you say Na over 1 plus 1 over G. So now is the degeneracy factor here. Silicon got 4. They say if you put 4, this one is half here. Then you do similar thing, and then you minus, and you get it. Okay, so the thing that I show here is not covered so it's actually not covered for your test or your final exam but just letting you know that these are this equation here if you want to know, some of you, if you want to check, and if what kind of question they can come out, and this type of question that we that may come out but since it's not covered, then it's okay So Rakin, you say that do we need to study book also for test 1? Yeah, if you study the book, then you can score If you study because you are well prepared, you study everything. If you don't study the book, then maybe the possibility you may face some problem in answering theoretical question justification why, all those sort of questions. But for calculation, I don't think any problem calculation, if you just study the lecture notes, I think it's good enough. But for theory, theory, there's much more theory in Newman's book than I show in the slides. Okay. Okay, next another term here called complete ionization. Complete ionization is very simple. Means that if you dope certain numbers of dopant, right, and all the dopant ionize, then it's complete ionization. It means that if you give a lot of acceptor and all these acceptor are ionized, then it's complete ionization. So it's very simple. The thing that you have to learn is how do you plot the Venn diagram, which is shown over here. So what is complete ionization? It is a condition where all donor atom, okay, donor atom, you have to answer both sides. You have to answer donor and then you have to answer acceptor. Donor atom positively charged. Why positively charged? They give up their electron, right? Electron jump to the conduction band, so now they are positively charged. And then you have to answer the other part. All acceptor are negative charged by accepting electron. Because they accept electron, then means that down there holes go down there, goes to valence band. You can say something like that. But you must answer for both sides. You cannot say complete ionization is when donor positive by giving donor electron. Although it's correct, but it's not complete, then you get half marks. If you answer both sides, talking about donor and acceptor, then okay lah. So complete ionization, even you read the terms, you already know what's the meaning. Everything ionized completely. Okay. Okay, so this is another one called freeze out. Okay, freeze out. So another, just by reading this, you already know is freezing temperature, and then there's another out. Okay, normally they say freeze out is at 0 Kelvin. All electrons in the lowest possible energy states. Nd plus equals to 0, Na plus equals to 0. So the condition that occurs in a semiconductor when temperature is lowered, maybe what they mean lowered here, if I lower up until 0 Kelvin, the donor and acceptor become neutrally charged. What do you mean neutrally charged? You mean that just now, right? Complete ionization, right? They have energy and then electron jump to the conduction band. Okay, but freeze out, which means that you don't have enough energy, so the electron all will not be ionized. So there will be neutrally charged lah. It will be like normal pristine. Actual original condition, they are not neutrally charged. And no, they are neutrally charged, but there are no charge over there. So it's like plus minus is equal to 0 lah. So 0, 0. The electron hole concentration become very small. Okay. Understand? Two different opposite scenario. One is complete ionization, one is freeze out. So charge neutrality. This is another word here. Charge. Okay, charge. Is it positive, negative charge? And then it's called neutral here. Charge neutrality condition in thermal equilibrium. Semiconductor crystal is electrically neutral. Okay, it means that if you don't it is like room temperature, you don't apply any external forces or potential, then they are electrically neutral. Okay, negative charge equals to positive. But determine the carrier concentration as a function of impurity doping and concentration. Okay, another term here. So we got many terms today. Compensated semiconductor. So in a semiconductor, normally, right, when you find that there is actually a donor, right, there is also an acceptor one. In a semiconductor, right, what you learn so far, right, you say that this is P-type only and this is N-type, right? You make it separate. But in actual semiconductor, right, they have both type, P-type and N-type together in a wafer or in a chip. They have both sides. They have both type. So normally in that semiconductor, you're calling it a compensated semiconductor. Okay, compensated. A semiconductor that contains both donor and acceptor at the same region. When you want to create a MOSFET, right? You got N MOSFET, you got P MOSFET, but they are putting together, you want to create an inverter, right? So they are compensated because both dopant and acceptor exist in the same semiconductor. So it says here that if your ND is more than your NA, donor is more than your NA, then you are essentially P-type. You cannot say P-type semiconductor. You say P-type compensated semiconductor because you got both here. Opposite, Na more than Nd, then is more like a P-type compensated semiconductor, and Nd is equals to Na, then is intrinsic. Okay, this is also the question that I used to ask in a final exam. I asked the student all to plot everything, charge neutrality condition. So when I mention charge neutrality condition, you must be able to plot everything. The one that you learn is NOPO. Okay, this one, the first one, and PO. All right, then what do you have? You have unionized. This is on freeze out one. This is on freeze out. And this one, you can say that this is on complete ionization, like this one. So all the positively charged because the electrons are donated, and negative charge because they accept electron, and positive go down here. So you got 1, 2, 3, 4 already, 5, 6. And then what else? Then you got plus and minus here. You have to draw another arrow here, and then you got so 1, 2, 3, 4, 5, 6, 7. And then 7. So you have to plot everything. If you miss out something, then you won't get full marks lah. But I will not tell you what to draw lah. I will not say that okay, make sure you got NOPO and all. But you need to know. You need to know that you got NOPO. What else? You got ionized for freeze out one. You got ionized for complete ionization, and then you got another one plus and minus here. Then there's a current can flow positively here, positive and negative. So this one also. To know more about this, you can read the Niemann's book. And charge neutrality condition, which means that neutral. So what it meant here is when you are this one plus this term, positive charge equals to negative charge. Negative charge because you are accepted. You can accepted the acceptor accept electron. Okay, then the negative charge plus with an O equals to PO, which is your whole concentration, plus with your, what is this, ionized donor, which is positively charged. Then you split this into two parts some more. This one is Na minus Pa. There's another word, Pa here. And then Nd, big Nd minus with small Nd. Okay. All right, so far okay. Let me check. Check here. So, okay, so this one is explaining how they get another equation for NO and another equation. You go down here, another for PO. So now you know that NOPO is what you learn, which is coming out in your test one, okay, which is this NO and PO. Okay, this NO and PO confirm, no problem. Okay, you must understand this. This is coming out. But later on, you have another NO and PO equation, which is incompensated. This is the derivation step that they show. In the end, you'll get this another NO equation where you put this one, the donor and acceptor, and you get another one called PO. This one is a PO, which is Na minus Nd. So now you got two way of writing your NO and two way of writing your PO. So if you have a question, say that if for your test one, which NO and PO is coming out? Is this NO and PO coming out or not? This NO and PO not coming out because this is after test one. Okay, this after test one, this not coming out. So before test one, before this NO, that is coming out, but this new one is not coming out. So they are trying to show that if it's a compensated electron, a compensated semiconductor, then what you have is that you're going to have a new equation, which is NO and PO. And this NO and PO, how do you do it? From this story here, NO, PO. So that's why they show here is, if you complete ionization, then if this one is PO, this Nd, then they're trying to solve it from here. Okay, when you assume complete ionization, what it means that all is ionized. Okay, so in your donor there's no more charge lah, because you're all ionized already. Then you say that this is, you cancel, you show this equation, NO equals to Na and PO equals to Nd. And what we found out just now is NOPO equals to Ni square. So they replace this PO with Ni square divided by NO. Okay, similarly. Then they move around. After what they do here is they try to move around, they get this NO And if you change this one to Ni squared divided by PO, then you're going to get another expression for PO. Okay, so this equation is quite simple. What you see here is that it's actually NO. NO is actually ND minus NA. If your Ni square is very small, let's say that this is very small, you can cancel this. And what you get here is you get, yeah, if your Ni is small, ND and NA is quite large, you can cancel this. So once you cancel this, you square root and square, you can cancel this part. So ND minus NA over 2 plus ND minus NA over 2, what do you get? You get ND minus NA if Ni is smaller than your ND and NA lah. Sorry, this one is. So if your Ni is small, you can just ignore this. It will be ND minus NA. But if situation where your ND, your donor as concentration, accepted concentration is the same, maybe this 10 to the power 9 and then this 10 to the power 8, then you cannot cancel it. Then you must include all this to calculate. So it's, for example, here, this one 10 to the power 16 and 10 to the power 10. Okay, 10 to the power 16, 10 to the power 10. So they say that can you minus them or not? Okay, let's see what will happen. ND 10 minus 10 divided by 2. Okay, you see, this situation here, I can say that it's quite small because this is 6 more than here. So if ND minus NA, right, is NO is, you can say ND minus NA lah. What is your NA? NA is 0. ND, what is that? 10 to the power 16, right? You see the answer. 10 to the power 16 is the same. You don't even have to write this equation. You just do in your mind only. You can get this answer. You just say ND minus NA because NA is 0. Your NO is actually your ND lah. Okay. Then for the second part, here, this is where all the student will make mistake. I'm telling you, this is when student calculated the NO part here, when they calculate PO, right, they do the mistake of, they say that PO equals to NA minus ND. This is what student will normally do. Happens every year. If you don't understand, right, they will do this silly mistake. And then what they get? They say that, oh, NA is actually 0, right? And then they minus 10 to the power 16 lah. And then last kali jawapan negative. Then do you think it makes sense or not when your answer is negative? It cannot be negative. Your doping concentration cannot be negative. So this is totally wrong. So how do you calculate your PO? You have to use this equation just now that we learned. Take the answer of intrinsic concentration, you square them up, divide by this answer that you found up there. So this is your intrinsic concentration, square, divide, then this is the answer. So this is NO and PO. Okay, when you use one of this formula, minus formula, then the other one you don't use minus anymore. You have to use this Ni square equation. Ni square equals to NOPO. If you say that what is Ni square equals to NOPO, I already mentioned to you just now, right? This one, NO and PO product. Me. Okay, important not to forget this. If you forget this, then you cannot do it. So that is why I'm saying that for your test one is actually very simple, because the equation that you use is not a lot, is few only. You don't have to use a lot of formula. Here, even for chapter 1, what kind of formula you'll be using? It's all basically general knowledge, sphere, volume, that kind of equation only, not difficult. And only the equation that you have to remember is only for chapter 4, where you have to know what is NO, PO, and NI, 3 only. Okay, for your test 2, okay, now it becomes difficult. Because for your test 2, you'll be learning more equation already by the time. Maybe for your test 2, it's cover chapter 4, 5, 6, and 7, 4 chapter. Then there will be a lot of equation. Okay, so every year for test 1, normally, student will score easily. They will get nearly full marks, or they will get full marks. Because if you don't take this opportunity to score for your test 1, Then by the time you go to test 2, it is more complicated already. It's more complicated, which means that it's not so as easy as test 1 lah. You have to put more effort on it. Okay, so I hope that you can take this opportunity. We're going to do test 1 next week. Then you may say that, oh sir, not enough time to rehearse and study. There's not much question. Chapter 1 is not straightforward only. Only chapter 2, you have to, it's just similar to your quiz. You have to learn NO and PO and NI. Okay, and then after that for the test 2, then this is where more equation will come in. You know that just now you have to calculate your NO, okay? Then it's actually similar lah. Once they do the same thing, they will repeat again for PO, and they say that, oh, to calculate PO, you just change the position only. Just now it was ND minus NA, right? So for your PO, you NA minus ND. Make sure that when whatever you do, you minus, right? You cannot get negative. If you get negative, right, how are you going to put inside here? How can you square root negative? You square root negative, you become imaginary. Then we become, that's wrong lah. Okay. Always remember when you minus has to be positive. If somehow you minus, you get negative, right? Which means that you're using the wrong formula. Okay, so for this similar here, you say 10 to the power 16, ND is 3 to the power 15. This is 10. So can you use your equation, just now the equation that we showed? Can. You just take NA minus ND, which means is 10 minus 7, then you get 3 lah. 10 minus 3, you get 7. See this answer here straight away. Don't even have to use this formula. 10, so 10 is 10 to the power 15. Minus 3, 15, then you get this answer. And then to calculate NO, you use this equation, NOPO, then you get this answer. So this is your two answer. So approximation, you can just say that your PO, if you don't want to use this, you can just NA minus ND, provided the situation. What situation you can use this? What situation? What condition? The condition must be, anybody can tell me what condition that you can use this equation?
Ni is small.
Yes, Ni is small. Very, very small. Okay, if your Ni is 10 to the power of 14, then I don't suggest you to use this formula because 14, 15, 16 is quite near to each other. 10 to the power of 10 and 15 still okay lah. You can use it. It's quite large. Okay, so then, oh, it's another one. What did I say here? Oh, it's a new equation. This one is a new equation that I change of Fermi energy. This is similar to what you, okay lah, this one is normal lah. This slide, actually I should put this slide before I introduce this one. So this one is coming out for your test 1 lah. Test 1. This is trying to show you, what is this? They're trying to introduce a new equation. N equals to Ni. And EFI, okay lah, nothing new here lah. It's actually quite similar. Okay, let's look at it. So this one is trying to tell you that how they change from here to there only. So in here, they introduce a new, they introduce this EFI here. They introduce 1 plus EFI, 1 minus EFI. Because plus and minus will cancel each other. Then this whole thing here, they will name it NI. Okay, this whole thing, they will name it MI. And then this back part, they will leave it and you get that thing lah. Not something new. It is actually shown. Let me check. There is actually shown here already. It just try to show you how do you get from here and there lah, to prove it lah. And I'm not asking you for your test 1 lah. This one, how to prove it, how to prove this one to get that one. If I were to ask you, then that's how you solve it lah. That's how you prove it to me. This is how you prove it lah, by substituting this to that lah. But I'm telling you, it's not coming out for your test 1, so you don't have to worry. Maybe for your final, who knows? So this equation, the same equation that we learned for NO and PO, what they do here is that they just change this NO here, they replace with ND minus NA. Okay, so they just replace this one only, not difficult. But they say that only valid when ND and NA is more than NI. Okay. Then this one similar, no problem. This also no problem here lah. This one is NO. Okay, this is nothing. And then if it's here, you can actually say that to calculate your PO here, you can actually take ND minus NA, provided ND and NA is more larger than NI. Okay, then you got another equation here. Okay, just trying to show you, nothing new, just all this equation. Probably the hard thing is that you need to sit down and memorize it lah. So let's look at an example here. We have a silicon, T equals 300. Then we got acceptor. Okay, acceptor is got Na 10 to the power 16. We have to determine the number concentration of donor impurity that must be added so that silicon is n-type and Fermi energy is 0.20. Okay, like I say that this kind of question, right? This kind of question is what you can expect lah for your final exam, because this question is not, it's like a reverse engineering. What they ask you is not so easy. You have to think about it, how to solve it. Did I solve it or not? Okay. So you say that how much you need to add so that your Fermi level will be 0.2 under your conduction band. So how much donor you have to add. So now you already got acceptor, but you need to add donor inside your semiconductor. So it means that maybe like adding salt and sugar like that. Salt and sugar you're adding together, but how much sugar you need to add? Similar, this kind of question. So in this situation, student, one thing they have to do is that what we defined earlier on here, what is an A and what is this equation here. So you have to put it here. Okay. So now how do you know that you can use this equation? Because this is 10 to the power 16. And for your silicon, your intrinsic, your Ni is 10 to the power of 1.5, 10 to the power of 10. So okay, you can use this formula. So you just reverse engineering, change here, change there, negative 0.2, put your NC in, and you get this, right? Student, what normally student would do, they say that this is the answer. Wrong. This is not the answer. This, you haven't completed the calculation yet. You have to say that ND minus NA equals to this one. Then how much ND? So this one you have to plus with your 10 to the power 16. Okay, you plus 10 to the power 16, which means 1, 1 times 10 to the power 16, you plus 1, then you get 2.24. So this ND, this is the answer. Okay, so this example is a very good example because it will make you think. Okay, so that is why I showed this previous two slides first. Because normally, if I just straight away jump to here without telling you how did I get ND minus NA, then student will get confused. They say that how can you just put PO equals to ND minus NA? And if student really do not know how to solve this thing, right, what they do is that they say that PO equals to the equation that we gonna come up for your test one, which is the NB exponential negative and then what is that? The EF minus EV. You cannot use this equation because this is the same equation. This is the same equation. You cannot use this equation put here. You cannot put yourself into your own self. So you have to find another alternate equation for PO, another alternate equation for NO. So where do you get this equation? This comes from your compensated equation. This is the compensated one. It comes from here. So you're putting two new equations into here and you solve your answer. Okay. All right. Then this is just a graph to show your position. Means that as the more you dope, right, you become more degenerate, and your Fermi energy will be nearer to your EC. Okay lah, makes sense lah. That will be nearer lah. In the more you dope, you will be nearer to your valence band lah, P-type. So what else? What else here? The more temperature, you see that position in front of temperature. If it's like here, okay, the conduction band here. If the temperature getting higher, then we'll be slightly away from the conduction band already. Temperature. If you're low temperature, then it'll be nearer to your valence of conduction band. So this is what's shown here. So this important term, we got intrinsic. That's one coming up. Extrinsic not coming out. Acceptor, atom, and you got donor atom. You learn the term complete ionization, you learn the term freeze out. And then the fundamental relationship is this one here. Okay, for your quiz 5 and 6 and 7, right? I already uploaded in your e-learning already, and then the due date is not this week. The due date like similar for your quiz, 3 and 4. The due date is this Friday. For your quiz 5, 6, 7, the due date is next Friday. Okay, so with that, I would like to know if you have any question or not, because we already finished your chapter 4. And those that haven't scanned yet, I'll give you the QR code now so you can scan, Mr. Attendant. If you have question on your test, I hope you can ask now, not ask like next class, or usually students like to ask 1 day or 2 days before the test. If you have any question, you ask now, I can answer for you. Right? If you ask 1 day or 2 day, right, you will get panic. And then you say that I wasn't aware of this, I wasn't aware of that. Okay, you have any question, feel free to ask now. Don't ask last minute lah. Okay, any question?